Hey everyone! In this video, we're going to be taking a look at the chain rule. So this is another rule that will allow us to find the derivative of certain kinds of functions. So in the past, we've already talked about other rules for derivatives, such as the product rule and the quotient rule. But now the chain rule is going to allow us to find the derivative of composite functions. So to start off with, let's just review what a composite function is. So a composite function is a combination of two or more functions. So let's say I have two functions, we'll say f of x and g of x. Now let's say we're going to set up a composite function, capital F of x. Our composite function, one notation we use for this, we use f of g of x. And what this means is I'm going to take one of my functions and I'm going to put it into my other function. The way that I have this one written, I'm going to take my function g of x and I'm going to plug that into my function f of x. So I have f of g of x. So g of x is inside f of x. I could also write this the other way. So I could say g of f of x. And in this case, f of x is going to go inside g of x. All right. Now, the chain rule is used to find the derivative of these kind of functions. And what we end up with, so the derivative of f prime of x, or the derivative of my composite function, what I get is f prime of g of x times the derivative of g of x. Now there's a lot of notation going on here, and it may be a little confusing at first. But one easy way that we can think about this is if I'm able to break it down into an outside function and an inside function. In this case here, I'm putting g of x inside f of x. So g of x is my inside function, f of x is my outside function. The chain rule is the derivative of the outside times the derivative of the inside. I can rewrite this in some other notation. So in Leibniz notation, we normally start off with y is equal to, so instead of f of x, so let's say y is equal to f of u, and then we're also going to say let u equal g of x. So same thing, just represented a little bit differently. So here g of x goes inside f of x, and that defines my function y. So then the derivative of this, we want to take the derivative of the outside function, so with the derivative of y. Here we're going to take that with respect to u, and then we're going to multiply that by the derivative of the inside function. The inside function was u, and we'll take the derivative with respect to x. So again, two different notations representing the same thing, but overall the chain rule is the derivative of the outside times the derivative of the inside. So now that we have the chain rule established, let's use this in some examples to make sense of it and talk about how to go through this process. So my first example, kind of a standard situation here. I have a function y is equal to x to the fourth minus 5x squared plus 6. And this is all raised to the fifth power. So this is a composite function where that trinomial inside the parentheses is one of my functions. And I'm taking that function and I'm raising it to the fifth power. So let's go through this one and we'll kind of use our Leibniz notation to do this. So the first thing, I'm going to define my variable u. So I'm going to say let u equal everything that's inside those parentheses. So x to the fourth minus 5x squared plus 6. And if I set up u to be equal to that, then I can actually rewrite my equation. I can say y is equal to u to the fifth power. So the way y is written now, it's really easy to find the derivative of that. I can simply use the power rule. I can also easily find the derivative of u by also using the power rule. Okay, So my chain rule, I need the derivative of the outside and the derivative of the inside. So the derivative of the outside, dy over du. So we're going to take the derivative of y with respect to u, because that's the variable I have in there now. So using the power rule, the 5 comes down out front, and then we subtract 1 from the exponent. So we end up with 5u to the 4th. Now I actually need to do one more thing here. U is not actually part of our equation, so we want to resubstitute back in our expression. So instead of u, let's plug in our trinomial. So our derivative of the outside, we have 5 times x to the 4th minus 5x squared plus 6 to the 4th power. So there's the derivative of the outside. We also need the derivative of the inside. So on the inside was what we defined to be u. So we'll do the derivative of u with respect to x. And again, like I said, we can easily find the derivative of this by also using the power rule. So the 4 comes down out front. We'll subtract 1 from the exponent. And then we have minus 5. The 2 comes down out front. So 5 times 2, we get minus 10 times x to the 1st. And the derivative of 6 is just 0. So then to finish up, the derivative of our equation, so y prime, this is equal to the derivative of the outside times the derivative of the inside. So what we end up with, the derivative of the outside was 5 times x to the 4th minus 5x squared plus 6 to the 4th power. And then we'll multiply that by the derivative of the inside, which was 4x cubed minus 10x. And there we go. So there's our derivative of our equation y. Let's do one more example just to go through that process one more time. So my second example, I have an equation y is equal to the square root of x squared plus 1. So first thing, I see here that we can actually rewrite this. So instead of writing this as the square root, let's rewrite this as x squared plus 1 to the 1/2 power. Now let's go through the same process using our chain rule to find the derivative. So I'm going to let u equal everything inside my parentheses again. So u is going to be equal to x squared plus 1. And that allows me to rewrite my equation as y is equal to u to the 1/2 power. And now we're going to find the derivative of both of these things. So the derivative of the outside, dy over du, again we can use the power rule. So the 1/2 comes down out front, and we subtract 1 from the exponent. So 1/2 times u to the negative 1/2 power. And just like we did in the last one, u was not actually part of our problem, so let's resubstitute. So here I end up with 1/2 times x squared plus 1 to the negative 1/2 power. I could simplify this a little bit right away. So instead of a negative exponent, and instead of the 1/2 power, why don't we rewrite this as 1 over 2 from our 1/2, and then we'll write this as x squared plus 1, and it's the square root of all of this. Okay, so that's the derivative of the outside. Now let's find the derivative of the inside. So the derivative of u with respect to x. And again, we can use the power rule. So the derivative of x squared is 2x. The derivative of 1 is just 0. So y prime is the derivative of the outside times the derivative of the inside. So what we end up with for our derivative is we have our fraction that we established here times the derivative of the inside, which is 2x. And to simplify this, we have a 2 in the numerator and a 2 in the denominator that will simplify. So our derivative is equal to x over the square root of x squared plus 1.